Am I audible? Hello?
Yes, sir.
Okay. Okay. Sorry for being late. So in this class, I'll start the discussion on shared memory and related to that, the problems that arise due to it, like the synchronization problems. So till now, what we found is if we so in a if there are two processes, so this is a parent process and say this is a child process created out of it. So this parent has forked this child. So what do you think? What entities this both parent and child will share? Is there anything that they will share?
No, sir.
Say if the parent wants to communicate something with the child, so how is it really possible based on the features or whatever you have? Uh, I mean, I have taught till now. Is it possible this child process, which has been forked by this parent process, can communicate with each other indirectly?
The signals.
Sir, through signals.
Signals is possible. What is the other option?
So some
Long back, yeah.
common file they have opened or something.
Yes, that's true. That is what I'm asking. So, if this is a file, say this is a file, and this file has been, say this file name is say xx.txt, and if this file has been opened by, I'm not talking about the syntax, but say this has been opened by parent, and after that, if it has forked this child process, I mean, so the child has been forked at this point. So automatically we know that in terms of the process data structures, the the file handler will be shared to the child, right? So in this case, as this particular parent can read and write something to this file using say fprintf or fscanf. So so even if there is no fopen statement, if it writes printf and all scanf, it will be able to access the same file. Okay, because say if this is a file pointer, say for example fp is a file pointer, so that's that same file pointer will have so this is a file pointer and this is a file pointer. So whenever the child has been created, the child will have its own file pointer like the parent, but the contents will be the same. So this file pointer will be pointing to this particular file, and when the child is created, it will have the pointer will have the same it will be pointing to the same uh, location of the file table, and because of that this child will also enjoy the access to the same file. Can you recall this part?
Yes, sir.
So what I mean, in fact the codes are both the same, the codes that is that the child has received from the parent, but what I mean to say is if the child has been created from this fork, so from this fork onwards, if there is no fopen, but if the child executes fprintf and fscanf, it will be able to access that. So if this happens, so if the parent writes say 20, the child can read 20, and if the child writes say 40 here, the parent can read 40, like this. So they can in some form they can communicate, and because they can communicate, using a common file that the parent has opened, it leads to what we found.
It's a race condition.
Rest
It may lead to, yeah, there is always a chance that the results of simultaneously updating some file record or some values, that may lead to some inconsistent results. So we don't know what is going to happen. So it was like account balance or whatever we have talked about. So this is one way of sharing through this, but there is a more straightforward way that a parent and child can communicate with each other. Okay, so is there anything that the parent and child share apart from file?
No, sir.
Probably not. So the global variables, it will have its global variables, it will have its own global variables. Maybe it will have the same values, but later on it changes here, but the change is not going to affect it because it will have a common copy. It will have its own copy, the global variables. The local variables, it's obviously it's a part of the function themselves. Now it will have, it has, if it has opened something in the heap segment, so the child will so the child also will have the same, but uh, it will have its own copy like that. So everything will be different. So the point is, in this case, if we want, we can this parent or whatever the processes are there, they may have a parent child relation or not, but they may, if they want, a process may create some particular uh, area or memory space which may be created by either this child or the parent, and which can be a specific or a special type of memory which is called shared memory. Okay, so this shared memory, as like normal memory, I mean when you call malloc or you call new, you just request for some memory. So this shared memory also, so there, if there are multiple processes like this, they may be parent child relation, or they may not have a parent child relation. So this is a parent, this is child, this is some other process, say maybe it is a, there may be some other process, say b. So among these four processes, nothing is common. If there is not a parent-child relation, there is no, there is nothing in common. So like A and B and A and this child, nothing in common. But some of these processes, parent, child, A, B, C, whatever, one of them, they may create a specific kind of memory, which is something special because it is a shared memory. Okay, and if it is a shared memory, then by some mechanisms we will see that, so this memory can be, once somebody has created, so others they can kind of subscribing or kind of attaching that memory segment to them. So if A creates such a special type of shared memory segment, and if some information of that is known to B, so B can get attached to it, this can get attached to it and all this, so like that. So once they get connected, or the better term that is used is they get attached to that shared memory. So once it is created and attached, so access to that space, that memory space, is as simple as that accessing a normal variable or a normal space in a heap. Okay, so if you create, if this A creates just a space for an integer variable in the shared segment, so this is a special segment, shared memory segment. So as like we are aware of heap segment, code segment, data segment, stack segment, this you can call it as a, this is a shared memory segment. Okay, so the idea is completely different. And if using some system calls, any process creates a shared memory segment, it will have some kind of identifier which, if others know, other processes know, even if they don't have a parent child relationship among themselves, those processes may try to get attached, or they may try to attach themselves to that particular shared memory segment, to that shared integer, again using some say system calls. And once this is done, then say if this space is maybe identified by say here it is identified by say n, so just writing n plus plus means it will be updated. But maybe this process once it has attached, it is trying to call it as small a. So if it is writes a minus minus, this gets, so whatever stored value is stored here will be decremented, something like this. So but this shared space which has been attached is identified by b as a say n, this as a, and like this. In fact they do it by using a pointer. So it will, so a pointer will actually point to it. So a pointer will actually point to it, and through that they can manipulate. And once it is done, the nice thing is this will be as simple as accessing a normal variable or a normal allocated dynamically allocated space. So is that part clear?
Sir, how can we prevent the race condition for
No, race condition is definitely not prevented. But first of all, I'm trying to say that what is the provision? I mean, what is the probable IPC, inter-process communication? One is the signal that you know, like using the files. There is a, it's a, it's not a very nice way of where the processes communicate, and it has got some restriction because only the parent and child can, if they want, they can communicate. But if there are two different processes which are no way related to parent child by parent child relationship, they cannot simply communicate. I mean, apart from signals, it's not possible. So we are just talking about enabling some other mechanism for process communication. One of them, this is one of the option, is to create a shared memory segment, and whoever creates, others they can attach to it, they can get attached to it, and they can all use it. Now definitely if you do so, it is your responsibility how to ensure process communication, how to avoid risk condition, that's a different thing. But the point is, before I get into those solving those issues, those problems that we repeatedly told earlier, let us see that how this shared memory can be created and attached, and it can be accessed. Is that part clear?
yes, sir.
This is another way of doing things. Like I mean, the the CAC department is there, the EC department is there, and then maybe some other departments are there. Now the departments want to communicate. So one way of communication is they can so the HOD can signal the other HOD by making a call and all this. This is possible. But another way is I think you have at least this batch you have been in our campus at least for 1 year, almost 1 year. So you know that how things are. So there is a tea stall. So that is close to the biotechnology department building and the in front of the computer science building. So maybe there is a board, or there is a notice board or kind of board which is shared piece. So anybody can write and others can read. Okay. So now maybe that the computer science department says that okay, the faculties of the different departments, they should so they should be able to communicate. Maybe that we have got a seminar this weekend, some interesting seminar. So we want to inform that to others. Okay. Or we just want to say that okay, we would like to have a seminar. So what is the preferred time? Just we put that information. Some EC department faculty or some other came and said that okay, we want to have it from 6 p.m. They just write in that board, and then some other time the CSC faculty comes and finds okay, they want to have it like this. EC comes, and so there is a kind of through that shared notice board. It's a shared notice board means it is not the notice board that is a part of the department. It's a in the shared space. So that is how it is different. Each department they are having the notice boards for their internal use. Now this is a different kind of notice board which is in the in a common space where somebody need to create, either the CAC or CAC department creates it. But once it is created, Others, if they want to get they want to get access, they will perform some mechanism. They say that we also would like to access it, and they use it like that. But once it is done, now there may be always conflict. There may be always race around condition and all this. So these things are there. We'll talk about. Okay. So here, so these are the okay. So if you have got the basics of what we are discussing, so can you just tell me that what can be the probable or how many functions, or I mean system calls, do you expect to get this shared memory functioning? What do you expect?
Sir, will you repeat the question?
My question is, if you have got the basic outline of what shared memory is, the purpose of it, so how many system calls or what type of system calls do you expect? What should be the purpose of the system calls? I'm not asking about the names, but what do you expect to be provided by the system, operating system, to enable such access or creation and all this?
Sir, a common address from where the.
See, address, whoever is creating, it will create the address. Address means some kind of ID, you can say.
Yes, sir.
That is fine. But my point is, uh, what should be the system call? So one system call should be to create it, right? Like creating that space should be, there should be one system call for that. What will be the other one? Somebody will call to create it. What will be the other one?
So other will be to linking for linking
Yes, so
the
linking or
memory.
attaching or something like that. Okay. So just creating does not complete the whole purpose. So then you have to get attached to it. So you have to just know that okay, it is there. That is one thing. What next? Once you attach it, once you create it and attach it, you see, so there is, so SHMGT stands for getting that, or getting means actual creation. SHMAT, it is meant for attaching. So a process gets attached to that particular shared resource or shared memory. And what is that? So as like attaching, you can at any point of time you can think that okay, I would like to get detached from that. That means the resource is still there, but the process willingly wants to get detached from that shared space, which it had previously it has attached. Okay. And then what? Destroy. These may be the case. Now for accessing, do you need anything else for accessing that space, reading, writing and all this?
No, sir.
Because as I mentioned, so nice thing is once you have done the creation and the attachment, now it is as simple as accessing a normal variable in a stack or in a heap. So that's a nice thing that happens, and everybody can do it in its own way. Okay. So the another maybe some interesting analogy can be like when you I think you people maybe may not be able to relate with this example, that's why. But say we have got different clubs, right? In our institute we have got different clubs. Say GNU lag is there, then the music club is there, drama club is there, maths club is there. So there are so many clubs. I think some of you have enrolled in some of those clubs, and before the activities start you had to leave. Okay, so some online activities are going on, but these clubs, they do have the fests once in a year. And these days, because of shortage of funds, I mean since last 2 3 years, what has happened? uh, Generally, just a minute. Say we have got this oval ground. Oval, can you recall oval ground?
Yes, sir.
And say this is GNU lug, this is say maths, and this is drama club, and this there are so many clubs. Now the thing is, now during the fest they would like to have uh, everything together. So like the college says that don't do so earlier, several years back. So the GNU lag used to have their own funds from the college. They will set up the arena and then they will have their all the programs and all, and they will dismantle everything. Then maybe after another 2 weeks, some other club starts again doing the same thing. So it's a huge wastage of funds and space, everything. So now what happens? Like they will do it in a central space in the probably in the same time, in the overlapping time. Say for example, GNU log wishes to create a common area where events or programs can be organized. So this is a common area. So this is that equivalent to that shared space, right? And they say that okay, we'll have some stage and all this, and we'll have the chairs, okay, where the students can sit, and there will be some vendors which will be selling things and all. So this whole thing will be, so this is the resource that they create, a common resource for organizing events, then uh, organizing cultural events, technical events and all, inauguration, valedictory, everything. Okay, so GNU log creates it. So it will have to call for that equivalent to that SHM GET. So who is going to do it? In a college, who is going to do it? So they will put the request to the college authority maybe, and the authority says that okay, so the estate department says that we'll take care of this, and using they will contact somebody, and this arena has been formed. So once it is formed, so just asking this common area to be created, asking the the college authority to get it done, does it mean that this club can start using it?
No, sir.
So then it will call, once it is done, then it will call SHM80. SHM80 means what? Now it says that okay, now we know that it is done, so I'll prepare it according to my own requirement. So if there are 100 chairs, they will say that okay, we'll have the chairs all arranged like this, okay, in a row like this. So they will make their own arrangements, or they will have the chairs arranged sometimes in small groups like this, so that they are organizing some group based event. So it is up to that. So they will attach with this, and they will figure out how they are going to utilize this space. But at the same time, the maths department, they are also sorry, that maths club or the drama club, they also want to use the same common arena. So what they what they expect, what do we expect from the drama club?
So they will also call SHM 80.
Now, will they call SHM get or 80? Which one?
So attach, sir.
Now, how do they know that SHM gate has been so it has been already created? Is there any communication between drama club and GNU club or all this? Because they are all independent, like so it is something equivalent to that, so like process A, process. So how can they know that the resource has been created? So the drama club, can it straightway call SHM80 expecting that is already there?
No, sir.
So what do you expect by the drama club to do? They will also simply ask the college authority that we have a fest, maybe as per the permission, both are overlapping, but anyway, I mean the next week we have a fest. We want some area which we can use probably, right? So they will also call SHM gate. SHM gate. So SHM gate is something like you are requesting the authority to get a certain area. So it may be in the oval, it may be somewhere, some other space, it may be in the sack. They do not bother. It is done. So once it is done, now the thing is, once it is created, so if the drama club also calls SHM GET, what do you expect? Will it be created once again?
No, sir.
So this, although they call it, but it will not, it will be ignored if it is created. So that is the case. So whoever wants to call it, get connected or attached to it, they will, each of them, they will call SHM GT and then SHM 80. So if it has been prior created, it will not be created once again. Now, how do they know that whether it is created? So that is the case. So they will have a global ID or a global identifier. Global identifier is required Say in this case it is called as the arena. So arena is a global identifier. So the GNU log says we want an arena. Drama club says arena. So arena is a global term. So everybody says that we want an arena. That's all. Now once it is there, now once they have attached to it, now they will, now when the GNU club wants, it will want it in different settings of the chairs. The drama wants a different settings of the chairs, like that. So they will all have their own way of setting up, and if there is no control over, so if there is conflict in the access time, so they will start fighting, right? So that is what we say the outcome is undesirable and anything can happen. Now once they have done it properly, so what they expect, SHM DT, right? They will get detached. So maybe that the drama club, they have got 1 day program, and the GNU log, they have got 3 days program. So drama club accesses it, and after 1 day it accesses, it says that okay, we are done. So they will inform the authority. In this case the authority is operating system. A process will inform that I am done, I am no longer using it. Okay, so once it is done, it's fine. Now what is the other so now GNU log also says that I want to detach maths also, and maths club and all this. So what is left now? A common facility got created, everybody got attached. When they have used, they have used. When they are done, they have detached. Is that enough?
Sir, we need to deallocate the memory also, sir.
It's not dialogue, it's like you have to destroy it, right? You have to destroy that. Destroy means, so again they will perform the unpacking, the decorators and whatever, the event manager, event management team, they will just unpack everything, clean up the whole thing and all this, so it will be released completely. Okay, so that is what is called as SHM CTL. Can you see this?
Yes.
So control means, so destroying is also a kind of control operation that we perform. So these are the 4 basic things, both 4 basic, processing or activities that is required for the shared memory. Is that part clear?
Yes, sir.
So probably it makes sense. So now let us just look into the, we'll now immediately get into the codes. So shared memory, what we say, it's a process can use inter-process communication IPC functions to create a range of address space that is also visible to other processes known as shared memory. So this one is, so a shared range of shared space is called a shared memory, and these other processes can be any other process. It may not be a child, or it may not be anything. This that may not have any relation with the process which has created. So the creator process and any other process can use the address space by attaching the same shared memory segment into their own address space. So just have to uh, uh, have some kind of pointers and something that will be pointing to that. So that is what is called they are attaching. All process can access, that means read or write onto these shared memory locations similar to normal variables. That is very important. Just as if the memory has been created by calling new or malloc. Okay, so to create we have got SHM get, and what are the things we have? The, you see, we have earlier talked about process ID, PID underscore T. You have already found the other kind of IDs that is used to keep track of threads, thread ID, T
Yes, sir.
thread underscore T. And here for this shared memory, this common or global ID that we are talking about every time, this one, this is known as a key. So it's a global key that we need to create. Okay, so that key, the identifier, or the type of that is known as key underscore T. Okay, so this is the global key through which all the other processes, they can identify that, or they can relate to that particular shared memory. What is this? So SHM gate is meant for creating that resource. So you have to say that what should be the key, global key of that you pass will be noted by the operating system. And then the size means how big should be that space. Are you going to create it for storing one integer, or it's an array of integers, or it will be an array of records? array of float, whatever. Okay, so you can just specify it as if it's a size of int or n into size of int, that means n number of integers, whatever. And then int SAGM flag. So there are flags. What do you expect? What can be the significance of the flags here? Can you guess? Whenever you are creating some resource, what kind of flags do you require? It's a memory. So whenever you are creating a memory, as a creator, you can say that
The
I would
default
like.
values.
No, I mean, but what type of values, what type of features should you mention in these flags? What can be the significance of the flags here? There is always a default, but what should be the use of these flags? How can you use the flags? Specifying the access rights, right?
Yes,
Like
sir.
when you create a file, you can say that the file is read only, the file is write only, the file is say read, write, execute, whatever. So in case of shared memory also the same thing happens, right? So when you are creating it, you just want to have it shared as a read only memory. That is possible. So CSE department wants to install a notice board or wants to have a shared notice board where they can only write, others they can read only. That's all. That's possible. So when
Yes, sir.
you create the notice board, you just put it in a glass cover and put a lock within that. That's all. So whatever the CS department writes, others they can read. They cannot modify. But if the CS department wants, it can be open notice board where anybody can write, anybody can read. So you are inviting conflicts. So that is up to you. So these SHM flags are something quite similar to that of how we specify access permissions in files. Have you used CH mode? The change mode, the mod CH mode 666777
Yes, sir.
in files.
Yes, sir.
So same thing can be done here while you create the shared memory. While you try to attach, what do you expect? You are trying to attach. So what do we expect?
So ID is required of the
So
memory.
whatever, see, the thing is whenever you are creating, you will have this integer, the whatever it returns is the ID, right? Using the key you create, but you get an ID. So that ID actually you pass. So it may happen that as a process, you create two or three such shared space. So one for having those inauguration and all this, one for having the online contests and all this. So where it requires, it's a kind of lab. So you have set up one lab for as a shared resource. You have created one maybe as a GNU lab. We have created one arena where the inauguration, the cultural events, the valedictory can go on, and another they have created space which is a kind of for giving talks, like keynote talks, invited talks and all this. So and each of them will, once they has been created successfully, they will be identified by a integer, by some ID. So when you are trying to attach, you should say that uh, if I am going to, so the process should say that which particular ID it wants to get attached. Okay, so for that this ID, so whatever it returns, it will be stored, it will be passed here. If it is just one, so the same thing, otherwise you have the option to which one to pass. And then what is this? So here you pass basically the some pointer variable which will be pointing to that particular space. So you have got a pointer in your local, in your own space, and that pointer will be pointing to that shared space. And there are also flags. Okay, and then when you detach, you just say that what to detach, that pointer, you say that okay, whatever it is pointing to, I would like to get detached. So no more, I mean, there is not too much to specify when you get detached. But when you are attaching, you should say that if there are many such shared resources created, so which ID you would like to attach, and the flag should be there. And when you are destroying, then what you do, you have to specify the again the ID, because you may have multiple such resources created. So you have to specify the ID. There should be some command maybe, and then So this one is the structure which stores the details of a particular shared resource. We'll see in details later on. Okay, so I think you have got some idea of what will be the use of this system calls.
Yes, sir.
So if you look into this a bit more in a bit more details, can you see this? The SHM means shared memory ID data structure. So this shared memory resource unit, the details of it will be stored in a structure, in a specifically defined structure by the system, and it will contain so many information. Can you see this here?
So the structure's name is SMHIDDS.
Underscore ds, yes, it
Understood.
has been defined by the system itself. We have nothing to do with it. So if you can, so you are passing the address. So I mean, you are passing a pointer and you are getting the value from it. So what you are passing here, you see. So if you retrieve it, you will get, or in other words, this structure, what it stores, you see, the operation permissions, then the number of size, the size of the segment. If it is, if you have allocated just a size of one integer, it will be returning 4. I mean, it will be storing the 4 here, segment size. This is SHM shared memory, SEG SZ shared memory segment size. Then this is SHM shared memory A time, that means attachment time. So when it got last attachment, because once created, then multiple processes at multiple times they would like to get attached to it, right? They get detached again, they get attached, so anything can happen. So the last attachment corresponding to some other process, maybe this process, when it has happened there, so it's a record that is maintained by the operating system corresponding to every such shared memories resources that has been created in the system. So last time when it got detached from some process, last time when it got changed because somebody has modified the values or contents of that, then it is like the PID of the creator. So the process which has created, you can find it out. PID of the last operator, so some other process which has operated. So that, and number of current attaches means, as I mentioned, so there may be 4 processes attached to it, or maybe 2 processes, like that. So maybe you can check this whether there is any process which got attached yet. If the number of attachment is just 1, that means you are the only one. Only then you can call shmctl to destroy. If you find that the number of shm in attach is more than 1, that means that somebody else also is using, so you should not try to destroy it. Okay, maybe the drama club has completed their fest, but maybe the GNU club is still continuing. So you should know that how many clubs they have actually subscribed or they have opted for attaching to this particular area.
So
Is that fine?
when number of current attaches is 0, then it's safe to
No,
destroy.
0 means the process itself. So the process who is going to call SHMCTL, it is already there. So you should take in yourself also into account. So it should be 1 at least. It cannot be 0. 0 means how can that process be attached to it?
Okay, sir.
Okay. So this outline of a sample code. Is this visible?
Yes, sir.
See to the left here, so to the left you see it's a creator. I mean, we call it as a creator who is actually creating the shared memory space, and this is a user means, I mean, so we have executed this prior to this one. So this is a creator and we say this is a user of it. So what we are doing, and you can ignore this one, so the parameters passed in the main, you can simply ignore it right now. And can you see the key value, the global, so the key value, the global ID that will be used by all the other processes. So this is a global ID.
So that should be in hexadecimal.
Yes, in hexadecimal. So this is SHMKEY. We can use other notations also, but this is what is important. So this is the key value, and which must be known to all the processes those who are using. So the class decide that okay, we'll call that particular area as arena. Arena is the term that we use, or the the name that we use, and that everybody is aware of. So when you make a request, okay, I would like to prepare the arena, I would like to get the arena, attach, detach, or everything. So this is what is important. It's a global ID or a global number, global key, like that. Okay. Then what is this? You see local ID, then SHM ID. So there should be a local ID to the shared resource. Local ID means some identifier which a process is maintaining. So what is the first step? So SHMGET, can you see? SHMGET is the function, is the system call, and the first argument is just passing on the key value that everybody has agreed, and then you have specified the size. What is the size here? Size of int into 2. That means I would like to have space for 2 integers only. Okay, and then can you see this, the third argument, the flags?
Yes, sir.
So 0666, so this is not executable. Okay, so this is just merely read write access has been given to this these two space for these two for the integers, and then IPC create. So if you don't write here IPC create, so you cannot create it. So IPC create means you are going to create it, and if it has already been created, it will be ignored. That is what it means. Okay, so you can run this creator or this user, no matter, doesn't matter, but whoever runs it for the first time, it is physically created. If it is executed by some other process once again, it will be not once again created. So IPC create will make sure that the OS will not duplicate, will create a duplicate of it. Is that part clear?
So why do you use the logical or bitwise or operator, sir?
Okay, so that is all about, I mean, you have to see the man page and you have to figure out how they actually interpret that. Okay, so you can use some values also. So using those values, if you or it through the ORing, it will get a certain kind of information that what need to be done while you want to create. So the option, you can place your options during creation through this ORing operation. It is something like that clone. In the clone, you have the VM flags. Sorry, VM clone, then VM the clone underscore VM, then clone underscore uh, that those options are there. Sig hand. So for that details, you have to check the man page of SHM GET. Okay.
And since SHM key is decided by the user, so that's there's
Yes,
no.
yes. That need to be agreed upon in offline mode. Otherwise, how can you do that? There should be some kind of offline communication so that everybody knows it. Otherwise, how can they figure it out?
Yes.
Okay, so this is done. Now after that, attach, say SHMAT is that particular system call. Now I write. Can you see that SHMGT, whatever it returns, is stored in SHM ID. What is SHM ID? It's just an integer value. So whatever SHMGT returns, it's stored in a local variable in that particular process. And whenever you try to attach, you just mention your local ID. That's all. So once it is created and you get a local ID, you no longer use the global key. It's not required at all. Fine. For further reference in the remaining system calls. So now you say that SHMAT, SHMID, comma null, comma 0. So you are just sticking to the default values corresponding to these two. Say SHM address and this SHM flag. Again, if you are interested to know all the possible variations, you can go through the man page, because yeah, we have other topics to also discuss in this process synchronization. So this is just an idea that you can use some simple shared memory, and you can know how to use it and access it. That was and the flavor of having a shared piece of data as IPC mechanism. That is what I wanted here. But the different variations, you can either follow the book by Stevens, or you can follow any other the man page, or there are lots of examples in the internet tutorials where you get all the possible variants and variations of these flags. So now this I expect this to be a writer process. So this writer process, shared memory created and attached in the writer process. Now what I do, can you see this statement, what it says?
The type casting.
See, this shared memory is basically a pointer variable. It's a pointer to what?
The void pointers.
It's a void pointer, because so this SHMAT, whatever it returns, so it returns the maybe it you can say that it returns the base address of the space which has been created here and to which you are attaching. So if there is a shared space created, the base address will be actually pointed by this pointer, but you really do not know how you are going to use it. So it will be, so this step, you can think of this particular step is something equivalent to calling malloc or say calloc. The only difference is there you had those you had that space created in the from the heap segment, and here you get the space attached obtained from the shared memory segment. So there's a specific segment that is called shared memory segment. Is that okay?
Sir, internally, where exactly is the space allocated?
No, they, as I mentioned, so like the heap segment, data segment, code segment, stack segment, we have got the shared memory segment also. So this in your memory management, you have the each process will have the provision to have or maintain the shared memory. But in this case, the process may or may not be willing to get attached to it. So this is something maintained by the operating system as a whole, because this is not your own it is not your own property, it's not your own resource, it's a resource which you may create. So if you create something in the institute, if some club creates something in the SAC and says that I don't want to I don't allow others to use it, that's not fair. Okay, so through this SHM gate, if some resource is created, it is maintained as a part of the operating system resource. Got it? So other processes, they can attach to it. So they are not directly having, so each process is not directly having the entire details of that particular shared segment. So the operating system maintains it, that which particular pages it will maintain and all this, and will for the other processes it will just give access to it. Is that fine?
Yes, sir.
Yes, sir.
So because you see shared memory, you really do not know what will be the type. That's why you have declared void pointer. But now once you have got things attached like the malloc, so it is something like everything is just like malloc. So after you get the the base address of the entire space allocated, now you typecast it. So here also you typecast it here. Typecast it to integer and then assign it to x. What is x? X is now it's a integer pointer. So through this void pointer, you got the attachment and then you typecasted it to a integer pointer so that you can use the space to store integers. That's all. Now it might happen that your আমি ক্লাসে আছি তো কিছু থাকলে সই করে নিয়ে যা না আমার এখন কিছু নেই আচ্ছা ওটা করতে পারিনি আজকে কালকে দেবো আমি ক্লাসে আছি পরে করব হ্যাঁ হ্যাঁ ওকে so once the attachment is done, and once you know that, so after this part, you see, after this particular line, if you write, so what is x is actually pointing to the base address of that shared space. So the shared space maybe here. So it may happen that the shared space, so the shared space is here, and this x is actually pointing to this shared space, right? And it has organized the internal space as if it's a collection of integers. So once it has done so, so x0 means it can access the zeroth element, zeroth integer, then the first integer, second integer, like that. So it is, so this is the simplicity of use. So accessing the shared memory is just as if you are accessing normal space. But although you do so, you can be quite you should be aware that others also can use it simultaneously and create conflicts. So process one writer updated the value of the shared space. So it has stored 5 and 6, and it has displayed that I have written. Once it has done so, it has chosen to detach itself from that. So what it writes, shm dt, then shared memory, because now you see this shm, this shared memory and this x both actually points to it, right? So this shared memory, this pointer treats it as a void, as a un it's a unconfigured space, and this x treats it as a array of integers. So whenever you are trying to detach it, while detaching you just specify the pointer variable or the base address of that. You can see this, can you see this? So this
Yes,
is
sir.
enough. So you don't have to even specify the SHM ID, neither the key value. So detaching means just you say free. So this free, so this is equivalent to the free operation or the delete operation in the dynamic memory. But the only difference is, even though you free it, so you free yourself from that, but others may still get attached to it. That's the point. Fine.
Yes, sir.
So the number of attachments, like the in attach, once you execute it, it will be reduced by 1. It may not be 0. So process one writer detach. So what it does, so this creator process creates, or I mean, if it has been already created, it will just ignore it. It will attach, it will then typecast the memory, and it will just update something there, display, and it will detach it. And so maybe the process got uh, terminated after this, right? As you can see here, if we run it, shared memory created and attached, values updated, detached, like that. So at this moment, so let us see this, how it works. Let us see this, how it works. So here, can you see the same piece of code?
Yes.
It's modified some bit of it, but anyway, shmdt. So this is what it does. So it creates, this is shm get. Okay, so if this is id is -1, means it has not been created, so there is a error. Otherwise it is fine. Then it tries to attach with this writer process shared memory. This is the void pointer that I have named. And then after that, again, if every time if there is an error or not, I just check it to make sure there is no fault at the end. Then once it is done, then I typecast that to x and y. So x points to what, so you see x points to one of the element and y points to the other element. That is what I meant. So there's a little bit of change. So the same, so what I did here, the space for the two integers, I have tried to access it using two pointers. So one pointer points to the base address, another pointer points to the second element of that sequence of integers, and then asterisk x and asterisk y, that has been written. So I just checked whether it has been written properly or not. Hopefully it will be done, and then I just want to get detached from that straight away, but I don't want to destroy it. It's just detachment, that's all. So let's see whether
So
it
why you
works.
have done size of int writer process shared memory plus size of int? Won't it be one just plus one?
No, no, size of int means it will be skipping those number of bytes that is required for one integer, so that it will be pointing to the second element.
So but in array, let's say there is an array of 5 integers. So variable ARR points to the first element, but if we write ARR plus one, then that pointer is pointing to the second element. No?
Yes, so that's why. So how many bytes it will skip? It will skip the size of int number of bytes. So if you increment ARR plus plus, so will it be from the base point, from the base address, it will be adding just one to the base address?
No, sir.
It will be adding
Size
the
of it.
number of bytes equivalent to the element that is it is pointing to, right? So in this case it is integer. That's why I have written size of int. It's not just plus one.
Okay, yes, yes.
Got it?
Yes, sir.
Okay, so what was the name? Name was shared memory creator. So it wrote 5 or 6, whatever. Now, what do you think? Do you think that the shared memory still existing? Hmm?
No, sir.
Think that it's remaining in
Process
the,
one. Sir.
see, the process which created it got terminated. So do you expect? It's like after the event has been done, the class got the club got dissolved. So the club does not exist. The committee does not exist. So does it mean that the arena also will cease to exist?
No, sir.
It may not, right? So how to check it? How to check how many shared memory segments or how many shared memory resources is there in the system? For that, we need to type ipcs hyphen m. Can you see this? Can you see this? What it
Yes,
says?
sir.
Hyphen m means hyphen m stands for shared memory. So using this ipcs, you can see the existence of many such or other type of shared resources also. What are the shared resource? Message queue is one. So that is also one form of inter-process communication mechanism. You can consider semaphores, then message queues, then shared memory. These are all used for to enable inter-process communication, so that the processes can communicate with each other using some, definitely some protocols will be there, but to enable communication these are there. So IPCS hyphen m, it will show the number of memory segments. If I write IPCS hyphen s, the semaphores, is there any semaphore arrays?
No, sir.
No such exists, right? But we have just created one memory segment, that's why it exists. And mm, I think that was used by queue. Message queues also, there is no such queues, right? So what it's corresponding to each, what it shows? So the key value, can you see the key value, what we mentioned?
So 1, 2, 3, 4.
Then SHM ID, Can you see the SHM ID?
Yes, sir.
0.
This is just one is there. If we create multiple one, it will have different IDs. Owner is the my username. The permissions is 666 as we wanted. ORing with that. Number of bytes 2 integers. Number of attachment byte is 0. Is there any process which got connected to it?
So process 1 attached and then detached.
Detached. So is there any such any current attachment?
No, sir.
No, that's why it is. So the point to note is, even though nobody is attached to it, because it has been created and not wrapped up or not destroyed at the end, it remains there. Got it? So if I say before it get detached, if I write here for loop, what do you expect? It's running. So if you have got another, if you create another terminal and I write IPCS, what do you expect?
So in attached will be 1, sir.
Got it?
Yes.
Now so it is there, it is running. Okay, so now let us do this, that I do not, so I would like to create but not destroy, or maybe I would like to create something like 3 5 3 4 3 5. I would like to create one more. Now can you see that although the process got terminated, so I terminate the process, will it still remain? Still remains, right?
Yes, sir.
Now I again run the I again compile it. Now I am going to create another resource with a different name, right? So can I see that if there exists or not? What happened? Hmm. Okay, I think I'll check it and answer. So bytes are 8 and attachments are 0 now because I have not uh, included that for loop. Okay, let's see the user process. So although the creator has created it and it has written some values 5 and 6, this is the writer, right? Sorry, this is the reader. So in the reader process, you see the same thing has happened. It has tried to uh, get it or create it, but because it is already created, so it will not be created once again. And these are the two header files that you need to include to deal with the shared memory: ipc.h and shm.h. So IPC stands for all interprocess communication to deal with, and SHM specifically stands for a shared memory IPC. So then it is SHM 80, this one, then SHM memory. So you are having this attached, and then x0 x1, then you detach, and then you so then you would like to destroy this one. So let's see if I run how it works. Share memory, create. So got it? What it is reading? Hmm. Oh, this is no, this is memory user. Okay, this I have to run. Share memory. Got it? This code?
Yes, sir.
I mistyped it earlier. So this is the case. So I've used the same key, and now it has read. So it has not written 5 or 6 anything, but it successfully read it because some other process wrote the values for it. Now if I now run this, let's see what is output. Is it, does it exist?
No, sir.
Because this process, after reading, it has successfully destroyed it also by calling shmctl. So there you see, now once this during detachment you have used the pointer variable, the base address, which is of no longer in any use. So that's why after you detach, so till you detach you can use the pointer to refer to it everywhere, but once you have detached, now you have to again start using the shm id, the local id that has been given. Okay, so the globally it is known as shm through that shm key. Locally, before attachment or detachment, it is known as shm id, I mean through some local id. And if you have attached it, you can always refer to that space through that pointer. Is that okay?
Yes, sir.
Now if both of them they would like to update and modify, so what I mean is that file, the anomaly that arises in the file operation, like the account balance, you can do it using a shared memory also. You can repeat the same experiment using shared memory and see that after say 1 lakh updates, 1 lakh updates by the process 1 and the process 2, seems to be the two say account holder processes. So how many, what is the actual value? So will it from starting from 0, will it finally have the value of 2 lakh, or it will be having something less or more or whatever, so that you can check.
So
So
what if we don't deallocate the shared memory and we want to
it will remain as a
deallocate through the terminal?
yeah, it will remain as a garbage in the system. Garbage means anybody else can use. So if you are having some shared memory segment for some known purpose, so like in case of heap, if you allocate something, you should deallocate something. But in this case, even the process ends, because it's a you have created something for the entire system for all other processes. So if nobody is taker, so it will remain there. And if you are really aware that nobody is going to use it except you and your child processes, so it's better you should use that shmctrl to destroy it. Okay,
Yes, sir.
so I think we have discussed about the use of the, I mean how you can create shared space. Okay. So these are the topics. I think what's the time now? It is almost 5. So I'll take another 10 minutes of time just to brief the some of the basics, and then maybe tomorrow I'll take the class, continue the class. So I'll forward you these codes. Meanwhile, you can try to run these codes, and maybe that account balance code you can uh, run it using this shared memory and see the impact of it. It may not have the incorrect result, but it may have the incorrect result. If you run it for say 1 lakh times, you increment and see, it might happen. So in the threads, how they communicate? Two threads, how they communicate?
The similar port.
No, no. What is common? What is shared by default among the threads?
So the global and the static variables.
Yes, the global variables are there. If you have a global array, it can be done. But for processes, there were no such mechanisms till you have learned this shared memory, right?
Yes, sir.
So now just writing few lines of code, having a global key, you can still have the same thing there.
Yes, sir.
So by this time, I think you have known the sending signals through which processes can interact. Then using the files, parent and child can probably interact, though not in a very recommended way. Then while you are dealing with threads, lightweight processes, you know that using the global variables, you can have some inter-process communication, I mean inter-thread communication to be specific. And here you know that by using the shared memory segment, processes can communicate, right?
Yes, sir.
So all those known, now we'd like to get into um, the actual problem, the core of the problem, that how to deal with accessing shared variables. So how to create and define shared variable, now how to deal with the race condition. That is a big problem uh, that is left. And because in the operating systems, most of the resources are scarce. I mean, there are very few in number compared to the processes which will be willing to use it, and many of the resources are modifiable. They are not only just read only. So this allowing the resources to be shared in whatever form it is really dangerous until and unless you ensure some synchronization primitive or synchronization rules to do so. So this particular uh, so the next few lectures will be focusing on data access synchronization. So when you are accessing data in the shared space, what kind of synchronization would you like to ensure so that the race condition is never race condition never occurs. So the basic outlines, the assumptions, all this, and the algorithmic algorithmic approach, semaphores and all, everything we'll discuss about. Okay. So let me just quickly go through it. It is not very difficult, and maybe you will continue in the next class. So when we say two processes are interacting means what? So if Ri is the set of items that are the items, data items read by a process I, Wi is a set of data items modified by process I. So processes Pi and Pj are interacting. When we say it's interacting, if Ri union Wi, that means the read write space of process I overlaps with read write space of uh, Pj. It should be J. Sorry, this should be J. Okay. If this is not null, then we say the processes are interacting. Why interacting? Because through that overlapping space, overlapping memory space, they can interact. This implies that Pi and Pj share some data and both writes on it, either or either one writes on it and the other reads through it. So this is how they can interact. Okay. So the race condition we have earlier also we have mentioned. So just to uh, have some more details, because this is a problem that we'll be discussing right now. in the next few classes. So this is process pi which wants to modify ds as ds plus 10, and this process pj which wants to modify the same ds as ds plus 5. So what we write as shared, what I write here as shared int ds. Now you already know that how to what goes in the background to create such a shared integer, right? Is that fine?
Yes, sir.
So what things, so we have not got into those system call details. We say that okay, somehow both processes they have access to that shared integer named ds which is assigned the value 0. Internal details we ignore right now. So actually it comprises of many machine instructions: read, add and store. Now when you allow these both the processes pi and pj to run simultaneously to execute the statement, both are executing the same statement. So and each instruction will take some machine cycle, and they might so the ordering, so this ordering of this blue read add store, they should be one after the other, and the green read write store will be in the order, but these two might be mixed up. Okay, the relative ordering among the blue ones and the relative ordering among the red ones, they will follow some order, but uh, in between the orders, I mean you cannot predict in what sequence these instructions will be executed. So you can see that this read ds always comes before add ds, before store ds in all these cases. So that ordering is preserved. Same as the green ds, add ds and store ds also comes in that order, but whether both the red ds and then that we will not know. So the probable execution sequences in a uniprocessor environment where the all both the processes are bound to run all these machine cycles in the same processor, based on the scheduling, you really don't know what will be the in which order these green and red together will be executed, and as a result each of them will have a different outcome. Some will say 6, some will 11, some is 16 and 6. So what is the exact outcome that we expect? We have initialized it to 1. What is the what should be the exact outcome?
Sir, 16, sir.
16, because it is 1. So I would expect that this pi will increment it to by 10, so it will be 11 plus 5 16, or maybe 5 plus 1 6 plus 10 16, whatever. So this is the actual outcome that we expect, but it can be anything, and this is what is called race condition. Unknown outcome must be avoided, hence need for data access synchronization mechanism. Okay, so that is the need for data access. And in our codes, wherever we have got access to the shared memory, we call those sections of the code as critical. It's called a critical section of the code, and this is a very well known term and well used term in the context of process synchronization primitives. So critical section, better known as CS, is a code is one that deals with access to some shared resource R, hence should not be executed simultaneously with some other process. So if so in this case, this is the critical section, this instruction and this instruction both. So the critical section of two different processes should not be executed simultaneously to avoid conflicts and race conditions. That is obvious intuitive observation, right? And critical section CSR means, so this is associated with that particular resource R, a particular shared resource R. So if the critical sections are associated with a particular shared resource, then that should be avoided. So concurrent access or simultaneous access should be avoided. Okay, I think from this part we can continue in the next class, because this is more of a theoretical one, and so we have done the main practical part of it. Okay. Okay, one thing I just missed, it is this one, IPCS. So this command I'll show, and then that will be the end. So if I press IPCS hyphen M minus M minus I, can you see the details of it? So shared memory segment 0 ID, but it gives the details. So it basically stores, displays you the details of the SHM ID underscore DS data, that structure. Can you see this? The user
Yes,
ID, then the CID, CGID, then mode, access permissions, bytes. You see the last time when it was updated, changed, modified, and everything. So here also, if you say, if you can execute it using the system function call, you can dump it in a file, and you can then parse it and find out what who did it. Fine. So as a process, you may be interested to know that when that process has executed or something like, but you really don't know when you are just after you have read, immediately after that somebody has may have modified it. So if you want, these details can be visible if I use this command. So that is possible. Now after doing that, so at the theoretical part, we'll be talking about the semaphores. So semaphore is one a very interesting uh, primitive to ensure data access synchronization. So hopefully I'll be able to complete the theoretical part tomorrow, and semaphore maybe after the Diwali. And after the semaphore, we'll